Hello, my name is Matthew Mata, and this is my report for Lab 1, Motion at a Constant Velocity. For my observations, I took a video of a baseball moving across a flat bookshelf, and then putting it into Tracker, I followed the object's center of mass to get these coordinates and their corresponding times. So if you watch, you can see the object travel at what seems to be a constant velocity. Then, using this information, I was able to calculate the object's initial velocity using this, where the velocity equals the change in position, the change in the rate, divided by the change in time, equals the final position minus the initial position divided by the final time minus the initial time. Then, plugging in the data from Tracker, I was able to get the initial velocity to equal 0.52 meters per second in the positive x direction. And this came in handy for the v-idle predictions, where I was putting in the ball's mass, which is 0.148 kilograms, the ball's initial position, which is 0.002, and the ball's velocity, which I just said. And then I had to set up the calculation, where the time is set up so that it will end at the time where it ends in Tracker. And then I set the net force to 0 so as to allow me to view the object at a constant velocity. Then I had to predict the new velocity using Newton's second law, which pulled up here. The change in the velocity divided by the change in time equals the net force divided by the mass. And so, then using algebra, we can get this, where the change in velocity equals the net force divided by mass times the change in time, which we can equal out to the final velocity equals the net force divided by mass times the change in time plus the initial velocity. And so, in Python, we entered in this equation in the proper form, and so it should, once we run the module, it should predict the object's movement and see both this graph and also this ball moving across a flat plane. And so then, from the data we took from this that prediction that I just showed, we got a graph using Google Spreadsheets that shows the model, which is in the red, and then the experiment with the tracker, its position changing over time. And for the x-axis, we had the time and measurement of seconds, and for y it was the position and the measurement of meters. And so as you can see, there's a slight variance between the experiment's position and the model's positions. And this could be from a couple of things. It could be when I was following the object in Tracker and collecting the center of mass, I could have been off by a bit. There could have been, or there were other forces acting on the ball as it moved across that bookshelf, and I didn't take account for those, as I was thinking of it as there being no net forces. Then there is also the fact that it could have been at a non-constant velocity as it was moving. And so, what does all this mean? What do the models and predictions tell us? Well, they tell us exactly what Newton had figured out, and that's the object will travel or stay at rest at a constant velocity until acted upon by an outside force. And so, is it possible to find the net force, which is all the pushes and pulls that are acting upon the baseball? And from this video that I have in Tracker, that's not quite possible. Both because I also don't have the measurements of the wind going on in our house, and I also don't know how to calculate friction yet, as this is my first course. So what if we flipped the axis of the coordinate system? Well, if we flipped the axis, it would essentially change the direction the ball was heading in. It would, instead of in Tracker where it's going in the positive direction, say we flip this and it's set to go in the negative direction. Well, as you can see on this graph here, it goes in the negative x direction. So now, how is the origin of the coordinate system chosen? I put the origin of the coordinate system so that it was on the ball in its first frame, and it was heading in the positive x direction for easy measurement. And this is my lab report for motion at a constant velocity. Thank you for watching.